Welcome to this explainer. Imagine, just for a second, a world completely unrecognizable from our own. A world where land masses the size of modern continents are locked in this incredibly slow, agonizing billion-year dance. Today, we're diving into a place where the Earth's crust literally buckled and folded under unimaginable heat. We're talking vast tectonic plates colliding, ancient oceans disappearing entirely, and massive mountains rising and falling over eons. We're going to explore the awe-inspiring geological forces that shaped the Namibia region of southern India. So let's head deep underground and deep into geological time to see exactly what those violent forces left behind.
Now, to really grasp this region, we've got to understand what we're standing on, something called a suture zone. It sounds kind of surgical, right? But believe me, this is no simple fault line or a little crack in the dirt. A suture zone is a violent, ancient scar. It's the permanent mark left behind where two massive continental landmasses basically crashed into each other, crumpled up, and literally fused together over billions of years. Think of it as a graveyard for vanished oceans and the ultimate birthplace of extreme geology.
Okay, let's dive into this. Here is our agenda for today. First, we'll look at the Cauvery Suture Zone itself. Then we'll get into tectonics and how these continents collided. After that, metamorphism, or how these rocks were forged in fire. And finally, unearthing rare earth elements.
All right, let's kick things off with Section 1, the Cauvery Suture Zone. The sheer scale of what we're dealing with here is just staggering. The Cauvery Suture Zone is an east-west trending tectonic boundary stretching a massive 350 kilometers long. Just imagine that, a colossal 350-kilometer wall deep in the earth acting as a barrier between two entirely different ancient crustal blocks. Up north, you have the Archean Darwar Craton, which is some of the oldest, most stable rock on the entire planet. Down south, you've got the Proterozoic granulites of the Madurai Block. This zone, it's the chaotic tectonic blender where these two completely different worlds finally slammed into each other. That brings us to Section 2, Tectonics, Continents in Collision. Let's zoom in on our specific study area around Namibia, because this is where the story gets really violent.
You see, the landscape here wasn't shaped overnight. Geologists have uncovered this brutal three-stage deformation sequence. First up is D1, which is primary folding. Imagine taking a flat layer of rock and just squeezing it until it buckles into tight folds, creating what experts call geysisiosity. Then we get to D2, and wow, this is even more intense. This is coaxial isoclinal folding combined with a sinistral shear. Basically, the rocks weren't just being squeezed anymore, they were being violently torn and smeared sideways in a leftward motion, forming these incredibly tight hairpin-like shapes. Finally, there's D3. As these tortured rocks were pushed closer to the surface, they cooled off and became brittle. That caused broad warping and deep upper crustal fracturing. This whole crazy sequence of deformation perfectly tracks an epic clockwise PTT path. That stands for pressure, temperature, and time. The rocks of the Satyamangalam group literally went through it all. First was subduction, where they got dragged deep, deep down into the Earth's mantle. Next came accretion, violently scraping against other land masses. And then finally, a massive tectonic collision that crumpled them into the exact configurations we're looking at today. So what exactly happens to a rock when it's dragged down into those crushing depths? Let's get into Section 3, Metamorphism, Forged in Fire. We are now plunging deep underground. The pressure down here is absolutely crushing. And the heat? It's literally unfathomable. The rocks in the Namibia area experienced what geologists call peak ultra-high temperature, or UHT, metamorphism. We are talking about an environment exceeding 800 or 900 degrees Celsius. Conditions so unimaginably extreme that the original sedimentary rocks were completely cooked, melted down, and recrystallized into entirely new forms. When researchers placed these ancient, sandy, muddy rocks, which are known as samopelites, under a microscopic lens, they uncovered a hidden crystalline universe. They found diagnostic mineral assemblages that prove this UHT history. We're looking at beautiful, high-pressure minerals like garnet, silimonite, and orthopyroxene. But even more fascinating, they found evidence of sapphirine, spinel, and corundum forming at peak conditions. You see, these aren't just pretty rocks. They're essentially ancient thermal thermometers, proving to us just exactly how hot this tectonic oven actually got.
Let's move to and see how this builds because, well, what goes down must eventually come up. During that peak UHT metamorphism, those complex garnet sillimanite orthoperoxene assemblages formed. But as that immense tectonic pressure was finally released through a process called exhumation, the rocks began their long journey back toward the surface. This is known as post-peak decompression. As the pressure dropped, the rocks chemically retrogressed, meaning those high-pressure garnets and pyroxenes actually broke down and altered into totally new minerals like amphibole, plagioclase, and eventually biotite.
All right, let's shift gears a bit. Section 4, Unearthing Rare Earth Elements. So you have to ask yourself, after billions of years of being crushed, folded, melted, and forcefully pushed back to the surface, what did these extreme tectonic and metamorphic forces actually leave behind? Like, why is the Geological Survey mapping this specific region so meticulously right now? Well, this number right here is the answer, 1,365 parts per million. That is the peak total rare earth element concentration discovered in a single metaplite sample from the study area. In the high-stakes world of economic geology, let me tell you, that is a number that absolutely makes you sit up and pay attention. Let's break down exactly what the assay results revealed across the different rock types. In the younger granites, they found rare earth elements peaking at 773 ppm, specifically hanging out around these alunite zones. In the ancient, dark metapyroxenites, they targeted platinum group elements and found peaks of 54 parts per billion, right alongside physical evidence like malachite staining. And over in the metagabbro of the Metropolitan complex, they discovered significant values of chromium at 4,712 ppm and nickel at 743 ppm. Guys, these aren't just neat geological curiosities. These are the exact fundamental materials that power our smartphones, our electric vehicles, and tomorrow's green technologies. Now, what's really interesting about this slide is the staggering element concentrations hiding inside these rocks. In the pegmatite veins traversing the region, geologists found dark, glossy black crystals of a mineral called alunite. When they zapped these alunite zones with X-ray fluorescence, the anomalies were just off the charts. Look at these concentrations. Cerium at 5,300 ppm, bismuth at 3,250, lanthanum at 2,990, and neodymium, which is an absolutely crucial element for manufacturing powerful magnets, at 2,050 ppm. So the crucial point is understanding exactly how they got there. The survey report notes that these elements are heavily enriched in the banded migmatite gneiss, but depleted in the granite. What this tells us is an incredible story of remobilization. During all that intense heat and shearing we talked about earlier, superheated fluids literally mobilized these rare earth elements right out of the primary magma. They flowed through the tiny fractures and precipitated, concentrating themselves precisely in the contact zones where the different rock layers meet. That violent D2 folding we looked at, it actually created the perfect structural traps for tomorrow's most valuable resources. Which leaves us with a truly mind-bending perspective, doesn't it? The very screens we are looking at right now, the batteries that will power our future, they are entirely dependent on billion-year-old tectonic violence. If the ancient fiery scars of the Cauvery Suture zone hold the keys to tomorrow's technology, what other ancient secrets lie waiting, hidden deep beneath our feet? Thank you for joining me on this explainer, and remember to keep questioning the ground you walk on.